Hey y'all, welcome back. Today we're working on our homework, and really all we're working on today is trying to identify the different important characteristics of rational functions. So we're not quite graphing yet, we're not putting pencil to paper and like sketching out a graph. We're just going to identify the important characteristics, and in our next lesson we will learn how to take all those characteristics and put them on a graph to construct the complete picture. So on this homework, we're just finding one characteristic at a time. We're not finding all the characteristics for all these functions. So hopefully it won't take too long for you, but this first one is to find the zeros. Now, little tip here is the zeros really means the x-intercepts. Okay, these are the values of the function that make, the x values of the function that make the x, well, how should I say this? The numbers that I could substitute into x to make the whole thing equal 0. And so to find these, we're going to set the numerator equal to 0 and solve for x. Now, you want to be careful here. So I'll put a little note here. We want to check for holes, okay? Basically, if you've got a factor, or I'll say, if we've got an x value, that not only makes the numerator 0, but also makes the denominator 0, then that is not going to be a 0. Okay, so we want to check for those, which means that if we have a rational expression that's not already factored, we need to factor it first so that we can easily identify which ones are actually not going to be x-intercepts. So for this first one, it's already factored. There's no common factors here, so we don't need to worry about the holes. We're just going to set x minus 4 times x plus 1 equal to 0, and that gives us two x-intercepts, one at 4 and one at -1. So the way you typically are going to write your x-intercepts are as coordinates, so 4, 0 and -1, 0. For the next one, we are going to have to factor it. So let's factor this up front. This does have two factors, x minus 2 times x minus 1. And we get our first problem here that has a hole. So this is going to be, it's almost like they're trying to trick you here. You don't want to put 1 as an x-intercept here because that actually does not make the value of the function 0. It really only makes it undefined. Let's see, let's make this smaller so it can actually fit in here. We'll go one step smaller. Let's see if you can read that. Yeah, I guess that'll work. Okay, so we're going to ignore the x minus 1, and we're just going to set x minus 2 equal to 0. And so we're only going to get one x-intercept here, x equals 2. We do have another value if we were just looking at the numerator, without considering the holes, we would get this value of x equals 1. But because that also makes the denominator 0, we're not going to include that in our answer here. For the third one, we need to factor that as well. So let's go ahead and do that. The numerator is going to have, I might have to do this separately. And let's make this, I guess we don't have to make it as small because I'm running off the page anyway. So let's see, we need to first factor out an x. And that's going to give me x squared. Whoa, what the? X squared plus 4x minus 32. And then the denominator here is already factored. We don't need to worry about that. And so the numerator, we can factor a little bit further. Let's see, we're looking for two numbers that multiply to give me -32, but add up to 4. That's going to be +8 and -4. So we don't have any common factors between the numerator and the denominator. So we do not have to worry about the holes here. We're going to get a total of 3 zeros here. We're going to set this whole thing equal to 0 and then solve for x. So it does look like we're going to get 3 answers. It's going to be 3 x-intercepts here. We get one at x equals 0, one at x equals -8, and one at x equals 4. So our coordinates here are going to be 0, 0, which also happens to be the y-intercept. We're going to get -8, 0. And finally, we're going to get 4, 0. So we get 3 x-intercepts here. So that's it for the x-intercepts. The next section, we're looking for the y-intercepts. So to find the y-intercepts, what we're going to do is we're going to plug in 0 for x and evaluate. Now, you can go through and plug in 0 for all. Oh, are these the same functions? I guess they are. All right. So you can plug in 0 for each of the x's. If you've got it in standard form, like number 5 or number 6, really you could just look at these constants, okay, because the rest of this is just going to be 0. And it'll be a little bit easier to actually find the y-intercept. When it's like this, you can kind of bypass the whole plugging in 0 thing. So for number 4, though, it's not in standard form, and it's not really worth putting it into standard form. It's probably just going to be easier to plug in 0 here. So we get 0 minus 4 times 0 plus 1 over 0 squared minus 5 times x squared. I'm sorry, not x squared, just 0 plus 2. So we get negative 4 times 1 and negative 5 times 2, which is going to be negative 4 over negative 10. A negative divided by a negative is going to be positive, so it's just 4 over 10, or 2/5. So the y-intercept of this one will be 0, comma, 2/5. Now, like I was saying about 5 and 6, if your function is in standard form, if it's not factored out, it's actually easier to find the y-intercept, because if I just plug in 0 here, here, and here, all these are going to be 0, and you're just going to be left with these constants. So you really just need to look at the constants for the y-intercept. And so my y-intercept here is just going to be 2 over negative 1, which is going to be negative 2. And so my coordinate is going to be negative 2, I'm sorry, 0, comma, negative 2. And we could do the same thing for number 6, where we ignore all the terms that have an x, because when we plug in x, they're just going to be 0. So there's going to be like 0 plus 0 minus 0 minus 12. So that's just going to be negative 12. And then on the denominator, we've got 0 plus 6, so we just have 6. So just a little bit of a shortcut here if your function is in standard form. Works out pretty nice. So this one's negative 2 as well. Oh, that's weird. Wait a minute. Oh, wait, no, that's not the same as this. I was like, wait, gave me a pause for thought. Thought, wait a minute, I thought we were going to get the same thing, but no. All right, so, yeah, so what we get here is just 0, negative 2. A coincidence here that it's the same as 5, number 5. Don't read too much into that. You know, the y-intercept could be whatever. All right, so let's go on to the vertical asymptotes. So the vertical asymptotes, the way we find those is we're going to set the denominator. It's kind of like finding the x-intercepts, except we're setting the denominator equal to 0 and solving. But just, well, and just like with the x-intercepts, we need to check for holes. So up here, we had to check for holes because there might be a factor in the other side of the fraction that makes it equal 0 too. So we'll just double check for that, meaning we'll have to factor up front. Well, I guess number 7's already factored, but like number 8, we'll factor first and just see if we got an x minus 7 there. So we don't inadvertently call that a vertical asymptote when it's really a hole. So here, we're going to set x squared minus 3 times x squared minus 3 times x plus 5 squared. Set that equal to 0, and we can set each of those factors equal to 0 and solve them individually. So for this first one, I get x equals, if I add 3 and take the square root, I'm going to get plus or minus root 3. So plus or minus the square root of 3. Those are going to be 2 vertical asymptotes there. And then we get another one at x equals negative 5, right? If I subtract 5 from both sides, I'll get negative 5. So I get 3 vertical asymptotes here, and I'll just write them separately. So I get one at x equals positive root 3, one at x equals negative root 3, and one at x equals negative 5. And the reason why I'm writing it like this is because these vertical asymptotes are lines, and so the way that we express lines algebraically is with an equation. And so these will be the three equations of the three vertical asymptotes. Number 8 needs to be factored first, so we can check for those holes. So let's see, we got f of x equals x minus 7 over, how would this factor? So two numbers that multiply to give me negative 63 would add up to 2, would be negative 7 and 9. So we do end up, I kind of had a feeling that we would get a hole on one of these, and we do. We get a hole here at positive 7, and so the significance of that, as it pertains to this question, is that we can sort of ignore this negative 7 as we're finding the vertical asymptotes, because we know that it's actually going to be a hole there, not a vertical asymptote. So we'll just set the rest of the denominator equal to 0, and we get negative 9. And so, yeah, there's the equation of my asymptote. Number 5, this thing's good to go already. This is about as simple of a rational function as we can ask for. It's just x plus 2 equals 0, so we get x equals negative 2. So we get a vertical asymptote at negative 2. All right, so far we've talked about vertical asymptotes, x-intercepts, y-intercepts. The next category is going to be the horizontal asymptotes. So this is going to be a little bit more complex to just write here. What I guess I'll say is look at our notes for an explanation. And I'll kind of explain as we go, but it's just kind of too much to write in a small amount of space. That is not how you spell explanation. Explanation, there we go. So the sort of short version here is what we want to do is we want to look at the degree of each of the polynomials. So here we've got like 2 and 1, okay? Here we've got 1 and 2. Here we've got 3 and 3. And depending on which one's bigger, the numerator or the denominator's degree, we will determine what the horizontal asymptote is. So I'm just going to make a little template here and say the degree of the numerator and the degree of the denominator. And I'm going to have to make a note of that for each one of these. So for number 10, the degree of the numerator is 2 and the degree of the denominator is 1. So when the degree of the numerator is larger, we say there is no horizontal asymptote. So that'll just be true anytime the numerator has the larger degree. If the degree of the denominator is smaller, like in this one, so the degree of the denominator is 2, but the degree of the numerator is 1, then we're going to say that the horizontal asymptote is the x-axis, or y equals 0. And that's just going to be true no matter what else is going on. As long as the degree of the denominator is bigger, it's going to be y equals 0. Now, if the degrees are the same, so like in this case, we have the degree of the numerator is 3 and the degree of the denominator is 3. In this case, we look at the leading coefficients. Okay, so the coefficients of those leading terms. Here we've got 5 and we've got an implied 1. So the horizontal asymptote will be at 5 over 1, which is just 5. So we can write the equation of that asymptote. So it's going to be 5 units above the x-axis. Y equals 5. All right, so that's it for horizontal asymptotes. And for these last few problems, we're going to look for holes if there are any, which means we're going to have to factor these. So we'll just have a little factoring practice here. All right, so for the first one, the numerator will factor as x plus 3 times x plus 2. And the denominator, we can actually factor out at 2 as a GCF and get x plus 3. Okay, so we can see that we've got a common factor on the numerator and the denominator. So my x value is going to be negative 3. Okay, we're basically solving when x plus 3 equals 0. So we get x equals 3. X equals negative 3, rather. And to get the y coordinate of the hole, we need to come up with the whole equation, okay, that we talked about in the notes, which is if we cancel out the x plus 3's, then our y value is going to be x plus 2 over 2, and we will plug in negative 3 right here. Okay, so my y value will be, what would that be? Negative 1 over 2. And so the coordinate of the whole, try to put this so my head doesn't block it, negative 3, comma, negative 1/2. So we got a hole right here. For number 14, looks like we've got a cubic that needs to be factored using grouping here because we don't have a GCF to work with. So we can factor out an x out of the first two terms and get, or actually we can factor out an x squared, even easier, out of the first two terms to get x minus 2. And really the only thing we can factor out of the last two terms is 1. So we're going to get 1 times x minus 2 all over x minus 2. The denominator is already prime, so we don't have to factor that. Now, to get the two factors of that numerator, this whole factoring by grouping process, we're going to have x minus 2 as one of our factors, and then x squared plus 1 as the other factor. So the whole is going to happen at x minus 2, whenever that equals 0. So say x minus 2 equals 0. And so we know that the x coordinate of the whole is at 2. And the y coordinate of the whole is going to be whatever I get when I plug in 2 into whatever's left over. So if I cancel this out, I'm going to be left with y equals x squared plus 1. And I will plug in 2 right there. So I get 2, well, I'm sorry, I get 4 plus 1 is 5, so that's my y value, and so my coordinate is going to be 2, 5. And finally, on our last problem here, we've got a quartic that luckily has a GCF, so we don't have to factor by grouping here. The numerator doesn't have anything, so actually, we really don't even need to factor this one because there are no values that are going to make the numerator 0. But just for a little bit of factoring practice, I guess, we'll go ahead and factor this, assuming it's factorable further. But again, it's not really going to matter because we're not going to have any holes. All right, there's not going to be any factors that appear in the numerator and the denominator here. This one would factor as x minus 1 times x minus 1, so that'd be x minus 1 squared. But yeah, there's no value that makes the numerator 0 anyway, so we could have just stopped there and said, oh, there's going to be no holes. Okay, and the reason for that is there are no values, or no x values, I should say, that make the numerator equal 0. And I guess that's it. So pretty short homework for you guys. Hopefully you understand this a little bit better than when you started. But as always, let me know if you have any questions, and I'll try to help you out. And other than that, y'all have a great day, and I'll see you next time.